welcome everyone to this third day of the AAS virtual meeting. Each year, the Solar Physics Division of the AAS awards its most prestigious prize, the George Ellery Hale Prize, to a scientist for outstanding contributions over an extended period of time to the field of solar physics. I'm pleased to introduce Professor Kazunari Shibata, the 2020 Hale Prize winner. This is a particularly special occasion because 2020 marks the 50th anniversary of the Solar Physics Division. Because of the virtual format, normally I'd be able to present the medal and certificate in person, but Shibata-san is kindly giving his presentation from Japan. I believe it's 11 p.m. local time, so we appreciate that dedication. This is a photograph of the Hale Prize, again from the Solar Physics Division of the American Astronomical Society. We have also a certificate, and I'd just like to read the citation. So the citation reads, "For his outstanding work on the properties and behavior of magnetized solar and astrophysical plasmas, including the discovery of jets in the solar atmosphere, the development of original theories and numerical simulations of solar jets, spicules, and mass ejections, and the discovery of superflares on distant stars. Also of note is his significant role in the Yoko and Hinode missions, his mentorship of many PhD students and postdoctoral researchers, and his stewardship of the Kwasan and Hida observatories from 2004 to 2019. I'm really sorry that I can't present the medal and certificate in person, but those will be sent to Shibata-san very shortly. Shibata-san will talk about his research history spanning more than 40 years. His first interest was not actually solar physics, but active galactic nuclei and their jets. After recognizing that the sun produces jets, which was a phenomenon that he discovered and made popular, these jets are miniature versions of AGN jets, and so he became interested in solar physics. His work combines numerical MHD simulations and observations to study jet processes applicable to both the solar and astrophysical environments. So without further ado, I'd like to introduce Dr. Shibata's talk. It's From Jets to Superflares, Extraordinary Activity of Magnetized Plasmas in the Universe.
And for inviting me here to give a plenary talk in spite of the coronavirus peril. I am very honored to receive the Hale Prize. This is especially because the Hale Prize is the most important award on solar physics in the world, and also because I'm the first awardee of the Hale Prize from Japan. I'd like to thank the members of the selection committee, my friends and colleagues who wrote the recommendation letter, and all people who worked hard for this meeting, division, and the prize. And finally, I'm most grateful to my students and young colleagues during my career. Without their help, my research would not have been possible. Thank you very much. Okay, can I start my talk? Can you see my slide?
No, you'll just need to share your screen. Just click on the share button.
Okay, sorry. Okay, it's okay.
Thank you.
Okay. At first, I'd like to mention about the George Ellery Hale. He is my most respected role model as a solar physicist, of course, because he discovered magnetic field of sunspot, and also as a director of observatory, because he succeeded to construct several largest telescopes. And as a directory of Kwasan and Hida observatories, I tried to construct the largest telescopes in Japan with the help of donation by millionaire like George Hale. And also, I'm very happy to receive the Hale Prize because Professor Eugene Parker is a superhero for me on solar and cosmic MHD. And he is the first awardee of a Hale Prize in 1978 when I was a graduate student. This is a memorial photo with Professor Parker 30 years ago when I had a lot of hair. Okay, this is a plan of my today's talk. So let's begin my talk on the astrophysical jet. My dream when I was an undergraduate student in 1970s. This is my photo at that time. My dream was to resolve the puzzle of active galactic nuclei and their jets, the biggest puzzle in astrophysics in those days and probably even now. These are famous examples. Radio galaxy Cygnus A. You can see jets here, radio lobe. And also other example, quasar 3C273. And here you can see jets. In 1960s, many active galactic nuclei and jets have been discovered. And most of them, many of them are located at the cosmological distance. That means these are biggest explosion after Big Bang. And it was found that the AGNs are nucleus of young galaxies. This is the first astrophysical jet observed in 1918 by Curtis, famous M87 galaxy. Here you can see jets and nucleus. And in radio, we can see jet much more clearly, and also radio lobes. And these AGNs are very far from the Earth. Many are more than a few billion light years. So it seemed difficult to observe AGN directly. Hence, I thought I should take theoretical approach based on MHD, plasma theory, and solar physics, since the sun shows many jets similar to AGN jets. This is again M87 galaxies. And as observation developed more and more, we can see a smaller and smaller jets. And finally, we reached the nucleus. Last year, black hole shadow image was taken for the first time. It took more than 40 years to arrive at this stage, but nevertheless, still we have not yet seen jets. So I thought my strategy was right. And after 1980s, protostellar jets similar to AGN jets have been discovered in young stellar objects. And then these jets started to be called astrophysical jets. And this is a famous protostellar jet, HH1 and 2. You can see a jet here and shocks here and here. Length is about 1 light year, speed is about 100 kilometers per second. This is a radio galaxy, Cygnus A again. And in this case, length 3 times 10 to the 5th light years. The speed is 0.99 c, nearly light speed, very different. But nevertheless, these jets morphology is quite similar. So I thought there may be a common physics. Maybe in non-dimension, these objects may be explained by the same physics, hydrodynamics or magnetohydrodynamics. And what is the origin of astrophysical jet? This is a simple summary of characteristics of 3 kinds of astrophysical jets: active galactic nuclei, closed binary system, and young stellar object. central objects are very different. Jet length also very different. Jet velocity is very different. But it's very interesting that there is a common property that the jet velocity is comparable to the escape velocity of the central object. So suggests the possibility of unification. And it is well known that these objects, in these objects, a huge amount of plasma accretion occurs and forming accretion disks near the central object. So it's easy to imagine the energy source is gravitational energy. However, how to convert gravitational energy to kinetic energy of jets is a not easy question. What is acceleration and collimation mechanism of jets? And I thought there is a hint, useful hint from the sun. That is the magnetic field. In 1980s, Kurokawa-san at Hida Observatory of Kyoto University found very interesting spinning jets on the sun. Before eruption, we see helically twisted filament. This filament suddenly erupted, and then showing the interesting, strange velocity field in the blue shifted image and red shifted image. This is a combined image showing the red shift, blue shift. So this jets showing spinning motion. That is consistent with the unwinding direction of this helical twist. And so I and Uchida-san developed the MHD model we call magnetic twist jet. If helically twisted magnetic field is reconnected with the ambient field, then such a magnetic twist is released into open field, and that magnetic pressure in the twist accelerates plasma, also with rotation, unwinding rotation. How is such helical magnetic twist generated in the sun? In the case of the sun, we have a convection zone. Here, kinetic energy of turbulence is more than the magnetic energy. So magnetic flux tube is easily twisted. And once such a twisted flux tube emerges above the surface of the sun, and then reconnection occurs, we can have such a helical twist jet. In the case of accretion disk, much easier. Magnetic field is easily twisted by rotation of accretion disk. If the magnetic field is roughly perpendicular to the disk or parallel to the rotational disk. Such idea already has been proposed by Lovelace and Blandford in 1970s. But no one had performed time-dependent MHD simulation of astrophysical jets. In those days, some very nice steady self-similar model by Blandford Payne and numerical steady model by Sakurai-san. But we are the first to develop non-steady MHD simulation of astrophysical jets. This is the initial condition. Here is an accretion disk rotating around the central object. And if magnetic field is uniform and vertical to the disk, and then magnetic fields start to be twisted, and such magnetic twist propagate as a torsional alpha wave. And during the process, angular momentum is extracted by the magnetic field. And so accretion disk plasma continue to fall to the central object. And then magnetic twist becomes stronger and stronger, and finally magnetic pressure accelerates the jet along the rotational axis. And also a so-called magnetic centrifugal force can help acceleration because rotating field lines exert centrifugal force along field lines. And we found jet velocity is comparable to the rotational velocity of the disk, which is also comparable to the escape velocity of the central object. Therefore, this can be a unified model of astrophysical jets. And 10 years later, Matsumoto-san, Ryoji Matsumoto, my collaborator, first developed three-dimensional MHD simulation of the jet from rotating torus, and you see magnetic field lines. And also, it's interesting that disk shows the spiral pattern. And furthermore, Dr. Kudo and Dr. Koide joined our group, and we first developed the general relativistic MHD simulation of the jet from accretion disk around the black hole. And well, this is still not easy problem, but maybe applied to gamma burst jets. Many puzzles still remain, though more and more astrophysicists tend to agree with the importance of magnetic fields, I think. And please look at Roger Blandford's nice review last year. During the course of astrophysical jet study, I found Dr. Kudo's MHD code can be used also for the study of jet, spicule jets in the solar chromosphere. And I suggested him to do 1.5D MHD simulation along the flux tubes. We assumed some rotational perturbation at the foot point of the jet, like accretion disk. And then we found that alpha wave become nonlinear, and such nonlinearity produce a magnetic pressure force along the flux tubes, also generate slow mode MHD shocks. And so alpha wave can easily dissipate it eventually and accelerate plasma. And results explain spicules very well. And this is Hinode's excellent observation of solar spicules that reveal the ubiquitous existence of alpha waves on spicules. So consistent with this MHD model. And later, Suzuki, Takuya, Matsumoto, Shoda, Sakaue developed this model to explain not only spicules, but also coronary heating and solar wind. Then let's move on the subject of solar flare jets. As an introduction to solar flares, I will show you one special entertainment. This is a result of a collaboration with a musician, Kitaro-san, Grammy Award winner. This music expresses the ancient disaster, flood or storm. Now present disaster is the solar flares. This is a movie of the solar flares taken at Hida Observatory in H alpha. So you see two ribbons propagating. This is just before the very big flare observed by Hinode. You see sunspot shape is changing. Now magnetic energy is accumulating. And at the critical point, big solar flare occurred. This is a very large filament prominence eruption more than 30 years ago, taken at Hida Observatory in H alpha. The speed is more than 300 kilometers per second. this is the sun observed in soft X-rays by Yoko satellite. This is the time when the sunspot number is small. Actually, no sunspot. Here is a sunspot region, so we have many flares near sunspot. During the maximum time, there are many spots full of solar flares and ejections. So you can see a lot of thin structure all along the field lines. A very bright region is a flare with a temperature more than 10 million Kelvin. This is the artificial eclipse in space. Circle is the sun and occulting disk. You can see coronal mass ejection, prominence eruption. This is a famous big flare observed by extreme ultraviolet by trace American satellite. And you see flare loop height increase and increase. And sometimes you see the white dot. That is the result of collision of energetic particles in the CCD. This is a sunspot near the rim. And Hinode discovered many small flares, nanoflares and jets, chromospheric jets near a sunspot. And later I will discuss all these jets are a result of reconnection. This is again famous prominence eruption and flares and energetic particles observed by trace in extreme ultraviolet. This is the size of the Earth. This shows a famous prominence eruption, very interesting, strange prominence eruption. You can see the prominence plasma is fragmented and fall onto the surface of the sun. And this fragmentation is probably Rayleigh Taylor instability without Rayleigh Taylor. The same one in the different wavelengths. And you can see this filament is similar to, for example, Crab Nebula filament. And once again, please look at the waves from this filament eruption. This waves are shock wave. So the shock wave eventually propagates to the Earth and give some disaster. This is the largest prominence eruption in the history observed at the United States, more than 70 years ago. And you can see helical structure. So this is evidence of a helical magnetic field. And this is the more recent prominence eruption observed by Hinode. This is a big X-class flare observed at Hida Observatory in H-alpha. You can see two ribbon and a filament eruption. This is the same flare in EUV observed by SDO satellite. You can see prominence eruption and the bright flare in roughly plasma 1 million Kelvin. Same flare in H-alpha, the temperature 10,000 Kelvin or so. So comparing both, we can analyze the physical structure of the jets. This coronal mass ejection is an extension of the previous prominence eruption. So this prominence eruption become coronal mass ejection. This is another event, but showing the blast wave is attacking the Earth observed by stereo. This is again soft X-ray movies taken by Yoko. Yoko is a Japan, US, and UK collaboration mission. So did you enjoy? If you want to see the movie once again, please buy this on Amazon. Okay, let's discuss the mechanism of solar flares. In 1960s to 70s, several solar physicists developed so-called standard flare model by Carmichael, Starrock, Hirayama, and Kopp and Newman. And according to their model, at first, before onset, filament is formed. Filament structure is a sheared field. That means the electric current is flowing along the field lines. And after onset, such a sheared field or eventually helical magnetic field erupted, like previous largest prominence eruption. And below the prominence, we have anti-parallel magnetic field, current sheet. And then magnetic reconnection occur here, releasing magnetic energy to heat plasma as well as accelerate plasma. And Yoko, in those days, there are many anti-reconnection solar physicists in the world because there was not enough observational evidence of reconnection. But after Yoko launch, Yoko soft X-ray telescope discovered a lot of evidence of magnetic reconnection. This is a simultaneous H-alpha and X-ray image of one big flare. Here is a two ribbon flare in H-alpha. And the Yoko reveals that this kind of type of structure that is a cusp-shaped coronal loop above H-alpha ribbons. So this is excellently agree with the predicted structure of the solar flare from reconnection model, like this. So this kind of observation established reconnection model, at least phenomenologically. And furthermore, Yoko discovered ubiquitous existence of plasmoid ejections in various kinds of flares, from small impulsive flares of the order of 10 to the 9th centimeter to long duration event flares, 10 to the 10th centimeter, and even for the coronal mass ejection event, Yoko X-ray telescopes discovered a giant arcade, even if X-ray intensity is weak. But giant arcade is basically similar to this cusp-shaped magnetic loop. So I started to propose unified model of flares. And in this model, I emphasize the importance of the role of plasmoid ejection. After the plasmoid ejection, we can have a strong inflow into the reconnection point. That enhances the reconnection rate very much. So I call this plasmoid-induced reconnection. And on the other hand, Yoko satellite discovered also small scale coronal X-ray jets from small flares, micro flares. And Shimojo-san made a very nice statistical study and found evidence of magnetic reconnection at the foot point of the jet. By the way, this foot point often looks like this one. So we start to call this anemone jet because this is similar to sea anemone. And Yokoyama-san developed a very nice MHD simulation model for this type of jet. based on the reconnection model. And this is one typical example of MHD simulation of reconnection associated with the emerging flux. And as you see, this lines are magnetic field lines, and color shows the temperature distribution. Here is the corona, and here is the chromosphere. And when the magnetic group rise due to magnetic pressure to collide with the anti-parallel magnetic field line, we have a current sheet here. And once reconnection occurs, you can see plasma is suddenly accelerated by magnetic tension force. So we call this a slingshot-like effect. And also you see the plasmoid magnetic island is created and ejected. And in 3 dimensions, these islands are helical magnetic filament or flux rope. And also we see that in this case, both hot jet and cool chromospheric jets are accelerated simultaneously. And 10 years later, Hinode satellite, again Japan, US, UK mission, discovered ubiquitous chromospheric anemone jet. Morphology is quite similar to coronal X-ray jet, but spatial size is more than 1/10 smaller than coronal jet. And this means this has evidence of magnetic reconnection at the foot point. And summarizing observations of various flares and jets, from small flares, micro flares, to giant arcays, spatial scale is very different, more than 1,000 times. The lifetime is also very different, but it's very interesting that if we normalize the lifetime by Alphen time, then non-dimensional time scale is comparable to 100 in all different phenomena. So this suggests a possibility of unification by MHD. But the shape of mass ejection is very different. In the case of small flares, we see only jet or cool jet called surge. But in the case of larger flares, we have plasmoid ejection or filament prominence eruption or coronal mass ejection. Very different. Why? This is my suggestion. In the case of large-scale flares, plasmoid or helical flux rope remain because this flux rope is ejected to a very low density interplanetary space. However, in a small scale flares, such a flux rope helical field filament soon collide with the ambient field, and then secondary reconnection occurs, and such a plasmoid or filament eventually disappear to have only helical jet or Alphen waves. And more recent observation by Hinode confirmed this type of unification of a jet and flares. However, we have still basic puzzle on reconnection. That is, what determines the reconnection rate? How can we reach such small scale to lead to anomalous resistivity or collision-less reconnection in solar flares? And in order to answer the question, we started to propose plasmoid-induced reconnection and fractal reconnection with Tanuma and Tajima-san. A hint is come from the hard X-ray, the microwave observation. That is, when we have a higher time resolution observation, bursts show similar time variation in a shorter and shorter time scale. So fractal-like. So we thought this may be the result of a spatial structure is also fractal-like, because MHD is basically scale-free physics. So This fractal structure enables to connect micro and macro scale structure dynamics. And MHD simulation also show plasmoid-induced reconnection in a fractal current sheet. And as the thinner and thinner current sheet created, we have a smaller and smaller plasmoid. This means shorter and shorter bursts. And more recently, Takasao-san discovered multiple plasmoid in a flare current sheet. And now such kind of a small scale structure, plasmoid structure, started to be observed in many solar flares. And this fractal reconnection is very useful for particle acceleration mechanism because when the plasmoid collide with the fast shock at the rooftop of a flare, we have a Fermi type acceleration. And if this current sheet is a fractal, we have many different sizes of plasmoid. So even if single collision do not show power law distribution of energy, but fractal distribution plasmoid eventually leads to power law distribution for particle energy. And finally, I will introduce the superflares on solar type stars. This is a famous occurrence frequency of solar flares, microflares, even nanoflares, showing the beautiful power law distribution as a function of energy. And this is the largest solar flares observed. And we call even larger flares superflares. And whether superflares occur or not, very important for our Earth and the civilization. And if these statistics continue to larger superflares, the frequency is very low, once in 100 years or 1,000 years or so. And such a superflare may have affected the origin and the evolution of life in the past on the Earth. And on the other hand, X-ray astronomy reveals young stars show superflares with energy 1 million times more energetic than the largest solar flares. By the way, in 1996, we tried to model the protostellar flares and jets by extending previous astrophysical jet model. This is a planet-forming disk interacting with the dipole field of a star. And eventually, this interaction leads to the ejection of a huge magnetic loop, like very similar to coronal mass ejection. And the connection occurs here, creating superflares. And further, Uehara, my student, extended this model to a much larger scale and found that this coronal mass ejection finally became jet collimated by magnetic pinch. And people believed present sun is not young, so and slowly rotating, so would not produce superflares. However, Maihara et al. Discovered amazing result. Maybe better to skip this one. Using Kepler satellite data, and Kepler observed more than 83,000 solar type stars. And the data are so large, so we asked the first year undergraduate student to help analyzing these stars because students have a lot of free time. And they are not familiar with astronomy, so they seriously searched for superflares. Then, surprisingly, they found more than 300 superflares on 148 solar type stars. And then the paper was published in Nature in 2012. And this is a typical example of superflares. This is a spike, is a superflare, showing the energy 10 to the 35 this is the other example. In this case, even larger, 10 to the 36 erg, 10,000 times more energetic than the largest solar flare. And we found all superflare stars show such time variation. Why? This is probably due to rotation of a star with a big star spot. This is a very big spot, but on these stars, probably such a huge spot may be present. And finally, we plot such superflare data here, previous figure, and then found more recently, Dr. Noto carefully analyzed the data and found that 10 to the 34 erg superflare may occur once in 500 years. So this is a very scary result. And finally, as I first mentioned, as a director of observatory, I tried to get funding from millionaire. And we fortunately succeeded to construct the first segmented mirror in Japan. And this is very useful to observe stellar flares. And in the last year, I, for the first time in my life, succeeded to observe stellar flare, M-dwarfs EV LAC, with the help of Dr. Maehara. And concluding my talk, the universe is full of explosion, flares and jets, and high energy particles from them. The reason why the universe is full of explosion is that the magnetized plasma is so unstable and active. Extreme activity such as superflares on the sun may have been related to the origin and evolution of life on the Earth, whereas it would be extremely dangerous for our civilization in near future. Thank you for your attention.
That's very great. Nice talk. It's really nice to see how solar physics can inform other astrophysics. It's a great laboratory for studying up close some phenomena that you cannot see elsewhere. We do have a number of questions here. First of all, the top vote getter was that the movie was great, gorgeous. So thank you very much for that movie and music. There's a question from Arnold Benz. What is the cause of superflares? What's the special condition? Is it the star, the special spot, some other special condition?
Mm-hmm. Yeah, the first important point is that we should have a very large spot. And then, that is a necessary condition, but not sufficient condition. In the case of solar flares, we already know that very complicated spot is a site of big flares, so-called delta type spot. That means N polarity and S polarity is mixed very much. And probably I suspect such is also true for stars, but we have not yet found evidence. But in future, we want to find such evidence of stellar delta type spot.
Okay, we also have a question from Ward Howard. It says, would plasma ejections be visible from superflares in other stars in light curves or spectra? Certainly you have seen them in light curves.
Yeah, now many astronomers try to detect prominence eruption or coronal mass ejection from stars in especially M-type active stars. And we also now looking for such evidence of mass ejection. And I think there is no very convincing evidence of that, but may be possible in future. That is a very important subject, I think.
Okay, maybe one last question. You mentioned at the very beginning of your talk, astrophysical jets have beautiful counterparts in radio. How about radio counterparts of solar jets?
Oh, this is a subject for you. Yeah, maybe you're better than me, but I can say that type 2, type 4 burst is a radio emitting plasma ejection. How do you think?
Well, I would say that whenever particles are accelerated, they will appear in radio. And so some jets, as you say, are cool surges. They probably don't have radio emission, but we certainly do see radio emission associated with some jets. And also type 3 bursts are associated from time to time.
Type 3 burst, yes, often associated with the jets. Okay. Yeah, thank you.
Okay, so I believe we're coming to the end of our time. I guess they will just cut us off when we run out of time. Let's see. Is there any analytical model in which reconnection plays a major role in launching, not just in collimating, large-scale astrophysical jets and outflows and accretion disks?
From observational point of view, I'm not so familiar, but theoretically, I can imagine several ways that the reconnection become very important. Actually, I always told my students to study reconnection in astrophysical jets. I remember there are several papers who reported the very bursty emission, non-thermal emission in those astrophysical jets, may be related to reconnection and so on. Yeah, would be an interesting future subject.
Here's a question in terms of the superflares seen in sun-like stars in Kepler. Those that show multiple superflares, are they different from those that are, may show just a single superflare?
Excuse me?
So so in stars that show multiple flares, are they different than the ones that show single flares during the time you've observed?
Yeah, I think even if a very active stars, many flare occurring, each flare is similar to other single flare. So, we had indirect evidence of reconnection for stellar flares. So, as I told you already, even in one flares, we have a lot of bursts, and each burst is a consequence of plasmoid-induced reconnection. So I think even inside the flares, we have a lot of small-scale flare or reconnection process. So, probably self-similar.
Here's a question. If there are superflares every 500 years or so, then there may be some historical record. Are you aware of any historical records of large flares?
Yes, that's a good question. Today I didn't have a time, so I skipped, but I have a slide here. One evidence is from carbon-14 in tree ring. Miyake-san young female researcher in Nagoya University discovered a sudden increase in carbon-14 around 77425. Now this is believed to be a result of solar superflares. And energy is around 10 to the 34 erg, so very consistent with the results of Dr. Notsu. And also other young researchers on literature discovered many evidence of big aurora observed in Japan. This is 200 years ago. Now we observed near Nagoya. Now it's not easy. We can see aurora in Nagoya or Kyoto, but in old days, such a large aurora was observed, even in such a southern part of Japan. So these are probably result of a superflare.
Very interesting. Here's another question about angular momentum. So do you think that helical jets can effectively transport angular momentum from their rotating host?
Mm-hmm. Yeah, and what's the question?
Yeah, do you think that the helical jets can effectively transport angular momentum away?
Yes, yes, yes. This is important. And of course, now we know that magnetorotational instability is another way to extract angular momentum. But if there's a global field and jets, we can extract angular momentum very efficiently. Yes.
Great. Here's another question. It's a great talk. What is the biggest remaining question you'd like to see early research, early career researchers focus on? Is there something that remains undone that you wish you'd had time to do?
Still, you say, I remember when I was child, before entering junior school, I wanted to know why I was born. You know? And now from this kind of research, especially superflare research, superflare may accelerate the evolution of life because of strong radiation and also lot of disturbance on the Earth. That is, of course, very scary and dangerous, but that may have an effect to accelerate evolution of life. So I want to know such possibility more. That is now a subject of astrobiology. So from astronomy, we may be able to find the answer why we were born. Okay.
Okay, you have very many questions. If you want to go through them after the talk, you can maybe answer by text. But I think we'll end it there. We very much appreciate this wonderful talk, and again, very much congratulations on this well-deserved Hale Prize. And we look forward to maybe better times when you can come and visit and present the material in person. So.
Yeah, I hope so.
Okay, thank you very much.
Thank you very much.